and I'm currently a second year student pursuing my BTech in Instrumentation and Control Engineering. It is my privilege to introduce to you our esteemed speaker for today's session, Mr. Alikhan Basheer, currently working as an optical engineer at the Indian Institute of Astrophysics, Bengaluru. He has completed his MTech in optical engineering from the prestigious Indian Institute of Space Science and Technology, Tirunelveli, and even made noteworthy achievements for his MTech project as a project trainee and intern at the Indian Space Research Organization, ISR. He has over a decade-long experience in dynamic fields such as electronics and communication, optics, mechanics, and instrumentation. He specializes in various areas like finite element modeling, image processing, data analysis, and large optics fabrication. India has been a key partner in 30-meter telescope TMT project since 2014, contributing 10% of the project's cost. Indian institutions including the IIA, ARIES, and IUCAA are actively involved in this initiative. India is responsible for developing 84 hexagonal mirror segments and the primary mirror support system SSA and the M1 control system M1CS, along with a significant portion of the telescope's control software. In this lecture, Mr. Bashir will be explaining more about the IAA's contribution towards the TMT project and the present activities happening at the TMT India and share his experiences as. On behalf of Nakshatra, I would like to extend my heartfelt gratitude to Mr. Bashir for taking time to take out of his busy schedule to share his valuable insights with us today. Sir, we are very excited to hear from you.
Yeah, thank you, Harish. Thank you, Gautam, for the nice intro. And thanks to the organizing committee to choose me for giving this presentation. So I was expecting some very senior professor to come for this kind of lectures. So I just have like some 10-year experience. So it's my honor to give a presentation to the enthusiastic students. So shall we start?
Yes, sir.
Yes, you may start.
Yeah. So good evening to all the students. So today I am going to give a presentation on the India and IAA. IAA is basically Indian Institute of Astrophysics role and contribution to the International 30-meter telescope project. So at least some of you might have heard about this 30-meter telescope. It is going to be one of the world's largest telescope, planned to be built in 2035. So I am fortunate to get a chance to work in this prestigious project. So basically, I will just give an introduction of what all things I am going to present. So first of all, I will just brief about my career path. So I don't think I need to give a detailed explanation since Gautam has already given an introduction. And then I will talk about the Indian Institute of Astrophysics, a basic introduction. Then I will talk about the observatories which IAA is operating. And then I will go into the 30-meter telescope project and how India is contributing to the project and what all are the facilities we have set up for making this reality, this project, and what all are the activities which is happening currently in the India across the country, and what all we have achieved and what stage we are in now. So as Gautam told, I completed my BTech in Electronics and Communication from Kerala, MG University. Then I did my MTech in Optical Engineering from Indian Institute of Space Science and Technology. So since this IAST is part of a ISRO, so I got a chance to take up my MTech project in one of the ISRO center. So I chose the Laboratory for Electro-Optic System, LEOS in Bangalore. So I did my MTech project, which is related to the stress mirror polishing, which is the technology used for making large segmented mirror telescope like TMT. So because of that, I got an internship in Indian Institute of Astrophysics immediately after completing the MTech. Then later I served various roles in Indian Institute of Astrophysics as engineer trainee, project engineer 1, project engineer 2, and then engineer B optics, which is my current designation. So When I say about Indian Institute of Astrophysics, it is basically a research institute established in 1971, and its main interest is in research in astronomy and astrophysics, and it is funded by Department of Science and Technology. If you look back, it origins to a earlier old observatory which is set up in Madras by British East India Company in 1786. Then IAA operates various ground-based observatories across the country, from southern part to the northern part, and some space-based observatories for the astrophysics research. And this is the main campus of IAA, which is set up in Koramangala, Bangalore. And basically, it's not like a college kind of infrastructure like NIT and all. Basically offers PhD, and it have a integrated MTech PhD in astronomical instrumentation for BTech and MSc graduates, and it has a direct PhD option also in astronomy and astrophysics for MSc graduates, basically physics graduates. And it also has a extended campus near Hoskote, which is 40 kilometers from Bangalore, where it houses various labs for the research and development. And it also has a control center for the Himalayan Chandran telescope, which is at Hanle in Ladakh. So basically, it is remotely controlled by a satellite from this Hoskote facility. And it also has a 100 class clean room, which is called as MGK Menon Laboratory for Space Science, where all the space missions, all the space telescope, all the space instruments are integrating and calibration will happen here. So recent Aditya L1 ISRO mission, it was integrated in here in this facility. And there was a earlier mission by ISRO and IAA, which is called AstroSat, which also calibrated and integrated inside this facility. Now recently, IAA built a optics fabrication facility, which is called as India TMT Optics Fabrication Facility, which we call it as ITOF, which is basically for the fabrication of large telescope mirrors. So I just brief about the IAS observatories. Basically, IAA has 4 ground-based observatory and 2 space-based observatory. One is in Kodaikanal Solar Observatory, which is established in 1899. And then is Vainubapu Observatory in Kavalur, Tamil Nadu. Then Gauribidanur Radio Observatory in Karnataka. Then Indian Astronomical Observatory in Hanle, Ladakh. Then space-based, we have a payload called Ultraviolet Imaging Telescope, UAT, in the AstroSat mission, which is launched in 2015. And we have a visible emission line coronagraph, VLC, in Aditya L1 mission, which was launched in last year. Then this is the Kodaikanal Solar Observatory. It was established in 1899, and it has a kind of solar data of almost 125 plus years, which is one of the longest continuous series of solar data available around the world. And it houses various telescopes like H-alpha telescope, Tin telescope, Warm telescope, Solar Tunnel telescope, and a Kodaikanal radio spectrograph. Then comes to the Vainubapu Observatory, which is located in Kavalur in Tamil Nadu. Might be around 4 or 5 hours journey from your campus. So it is actually open for the public. If you people are interested, you can have a one-day trip to the observatory. And it is actually open for public on Saturdays. So if you want to visit, you can contact me or some of the organizing people. So it basically houses 3 major telescopes, which is currently doing the observation. One is the Carl Zeiss telescope, which is a 1 meter class. Then we have a J.C. Bhattacharya telescope, which is 1.3 meter. And we have one of the largest telescope, Vainubapu telescope, which is 2.34 meter. This was the Asia's biggest telescope till 2014. So it is indigenously built in India in 1980s. And we have a Indian Astronomical Observatory, which is located in Hanle, Ladakh. It also houses a Himalayan Chandra telescope, which is 2 meter class. Then we have a Hagar Gamma Ray telescope and other growth and major atmospheric Serenkov experiment telescope, which is MACE. So these are the, and we have one more Gauribidanur Radio Observatory, This is jointly operated by Diamond Research Institute, Bangalore and Indian Institute of Astrophysics, and is operated since 1976. Then we have the space observatories, which is one is AstroSat, which is launched in 2015. This was India's first dedicated multi-wavelength space telescope. So this is not a single entity work. It was a collaborative effort of many institutes within our country and outside the country. Like ISRO was there, TAFR, IA Bangalore, RRI, Pune, Ayuka Pune, PRL Ahmedabad, like even Canadian Space Agency and University of Leicester. So it has 5 telescope in the AstroSat, and one of the telescope was built by IIA, which is Ultraviolet Imaging Telescope. So this was operation since 2015. We are getting really good results from this telescope. And recently we have a launch of Aditya L1, you people might be knowing. So this was India's first space solar observatory. In this mission also, IAA has developed its own payload, which is called the Visible Emission Line Coronagraph, or VLC. This is basically to study the solar corona and coronal mass ejection from the space. So as I told, we have observing the sun since 1899 from the ground. Now we have our own space telescope to study more detail into the sun's atmosphere. Now comes to the 30-meter telescope. So basically IAA involves in various projects within our country and outside the country. So we have several projects with ISRO, BARC, DRDO, and this kind of major institution. So one of the major project is this 30-meter telescope. It is an international consortium which is going to build the world's largest optical telescope. So when it started, 5 countries were part of the project: India, Japan, China, Canada, and USA. But due to some political reason, now China is kind of set back from this project. So right now, only 4 countries are contributing to this project. So India joined in 2014 as a full-time member. Even though we are a part of this from 2012 as a observer, as a full partner, we joined in 2014. So government approved for a 10% contribution to the project, so which was 1300 crore. The entire cost of the project was 13,000 crore. So one advantage with this project is almost 70% of the contribution we are giving to the project as in-kind contribution. So usually what happens whenever we join a project, they ask mainly the cash contribution. So we give the cash contribution, and as a return, we get the observation night. Suppose some 300 observable nights are there, we get the particular portion of the nights for the given cash contribution. But in TMT, the advantage is we are giving us in-kind contribution. So basically, we are giving components. So the advantage of doing this kind of contribution is it will develop our Indian industry, because we have to develop the industries, and it will get the knowledge of how to build a telescope. So it will help us to make future telescope. So that is the plan for India. So by being a partner of this kind of project, we'll get the knowledge of how a telescope works, because the biggest telescope we have is the Devastal optical telescope, which is 3-meter class. So we don't have a bigger telescope like 10-meter class or bigger than that. So by partnering with this kind of big, large telescope, we get the knowledge, and so with that we can make our own telescope. So that was the basic idea behind this partnership. So as I told, India is contributing 10% to the project. So one of the major contribution is towards the primary mirror. So this is the telescope structure. So whatever you are seeing, this dot, this is the primary mirror. So this primary mirror is having a diameter of 30 meters. So it is very difficult to build a single glass structure. This is made up of glass. So it is very difficult to make a single structure of glass with having a 30-meter diameter. So what we are doing, we are making small glass pieces, and we combine it together like a honeycomb structure, to act as a single platform. So it has to be precisely aligned to nanometer level precision so that the light will exactly focus on one particular point. So overall, the entire TMT consists of 492 segments and we have 82 spare segments. So these 492 segments are arranged in 6 sectors. So each sector will have 82 segments and 82 into 6. It will get 492. And we have another set of spare in case some maintenance time we have to replace the spare. So we have a 82 spare segment also. So out of the 584 total segments, including spare, 84 segments are supplied by India. This is as per the initial plan. So since China is kind of back off from the project, we may get China's share also. That still the discussion is going on. And this is the segment. So you can see this is the one segment. So the segment is very thin, so it cannot hold by its own. So we need a support system. So the whatever you are seeing at the bottom, this is the support system for this segment, which we call it as segment support system or segment support assembly. So each of the segment support assembly consists of 500 components. So this is one of the complicated item in this project. So and all the segment support assembly for the entire structure, India is contributing. So we have a contract with L&T Defense Coimbatore to make all the 584 segment support assemblies. And each of the segment support assemblies have 3 actuators. The green color box, this is the actuator. So basically, you can imagine all the segments are stacked very close. The gap between each segment is just 2.5 mm. So whenever there is a wind turbulence or some because of thermal distortion, the segment can have a small tilt. So that can affect our image. So the moment we have a tilt, we have some edge sensor. You can see in the picture, each edge of the mirror or segment, it is housed with a 2 edge sensor. One is here, one is at this side. Similarly, in the other edge also, it is having 2 edge sensor. So basically, the edge sensor will sense the deviation from its actual position and it will send a feedback to the telescope control system. So then this actuator will give the tip and tilt correction to the segment and it make into the proper alignment. So like each segment support assembly has 3 actuators and 12 edge sensors. So all the actuators like 17,100 and 1,752 actuators and 7,008 edge sensor and the cables, everything is supplied from India. And above that, the telescope control software, that is also India's responsibility. These are the major contribution. And in the second generation, equipments are there, instruments are there, like WFOs, HROs, these all are the instruments. So for the telescope to operate, these are also some of the parts of this telescope. These instruments are also India's contribution. So this is a cutout of the entire structure. So what you are seeing, this is the TMT primary mirror. So basically the light will come from the sky and it will reflect on this primary mirror. Then it will focus on the secondary mirror. Then the light will come to the tertiary mirror, which is at the center of this primary mirror. And this will focus the light into the instruments, which is at the platform. So this is kind of adjustable tertiary mirror. So we have different instruments there. So according to our application, we can use different instruments. We can tilt it to the different instruments and get the data. So this is the basic working of this TMT. So as I told, the entire primary mirror of the TMT, it looks like this. So it is divided into 6 sectors. Each sector is having 82 unique segments. We cannot, it's like a puzzle. We cannot interchange this to here, because this all are part of a puzzle. So each one is having its own unique description. So these 82s are entirely unique segments But if you see, all these other sectors are identical. So this sector is exactly copying this one. So this one. So we can change sector to sector. If one in this sector can be interchanged to the one in this sector. So that is allowed. But within 82, it is unique. If you see, even though it looks like a spherical curvature, it is not a spherical curvature. It is a hyperboloid with f number of 1. Then it is having a conic constant of minus 1.00953. Whenever we mention a conic, we have a conic constant. Then it is having a radius of curvature with 60 meter, and the sag, basically the depth, it is having 1.8 meter, and asphericity is of 29.3 millimeter. Asphericity is nothing but the deviation from a sphere. So that is 29.3 millimeter. Then, as I told, 492 segments are arranged in 6 sectors. Each sector contains 82 segments. So if you see how the TMT allocated these segments to each country, so this is the total map of this telescope. So this is just one portion of this. If you see the inner portion, the dark blue, this is given to Japan. And this light blue, which is given to the US. Excuse me. And the yellow part is our India's contribution. And the red one, this is China's contribution. So if you see, we have 12 different types of segment. This we have to make into 6 copy plus 1 spare. So that comes to 84 segments. So there are some talks going on to get the China's share also. One advantage with India is like our manpower is much cheaper compared to US or other countries. So when the project look into economically manufacture some of these segments, they will always come into India. So we already have a technology which is already proven. So the more chance that we will get this China's share also. So for making this telescope, India built a large optics fabrication facility in Hoskote, Bangalore, which is called as ITOF. So this is a world-class facility, especially exclusively for this segmented mirror telescope. So currently this telescope is being used for the 30-meter telescope polishing and integration. And in future, we will use this technology for our own Indian telescopes. So this technology is equipped with a special polishing technology, which is called as stress mirror polishing. So this is one of a unique polishing technology which will enhance the fast production rate. So if you see the conventional polishing technique, like the one we use for IAS telescope or ISRO's space telescope, we use the conventional technology. So the one problem with the conventional technology is that it takes a lot of time just for one mirror. So when I was in Leos for my internship MTech project, so they were doing the Cartosat 3 telescope mirror. So it took them almost 26 months to polish and do all the work of that primary mirror. So just 1.2 meter glass, it took almost 2 years. So you can imagine how much time it will take to make a 84 such segments, which is 1.52 meter, which is much bigger than 1.2 meter. So even 1 year, if you optimize, it will take another 84 years to complete all the 84. And imagine about total 584 segments. So it was very clear that we cannot use the old conventional technology to polish this kind of mirrors. So there was one company in USA, which is Coherent. So they have developed this technology and they made the telescope mirror for Keck telescope, which is in 1990. So they are the only company who have this technology right now. So the IA India was kind of agreed to get this technology through a technology transfer. So we paid almost 12.5 million US dollar to get this technology from the US. So all these equipments you are seeing is part of the technology. And as part of the contract, it was included that training also is included. So two people from India. So one was me and one of our senior engineer, Mr. Sriram. So we both went to US for almost 6 months, and we had exclusive training on this entire stress mirror polishing and from each and every aspect of the technology. And we learned the complete technology from there. And we came back to India and we transferred this technology to our own engineers and technicians in the ITOF. So basically, as I told, what is this stress mirror polishing? How it is making it very easy to build the grinding and polishing. So stress mirror polishing is also known as bend and polish technique. So assume this is our mirror. We have a flat mirror. We have to make a small curvature at the center. So in conventional technology, what we use a small tool polishing, and we go step by step to make the precise curvature in this. So since it is small tool polishing, it takes a lot of time to do the activity. But in stress mirror polishing, what it will do, this technology is only applicable for the thin mirrors. We cannot use this for thick mirror. So what it will do, it will bend the mirror in the conjugate of the shape. Whatever, suppose we need a curvature here, curve shape here, we bend the mirror from the edges. We apply force to the edges and bend the mirror to the opposite of the shape. And with the load or warp, we will do the polishing, make it to a flat polishing. We cut the surface. So with the stress we are doing this. So once the stress is removed, we get the conjugate of the shape. So this is the basic idea behind this stress mirror polishing. So here it is a very simple surface. So usually when we see the telescope mirror, it is having a complicated surface. So to make that kind of complicated surface, we need this kind of technology which can precisely warp the mirror in the conjugate of the shape we need. So this is the fixture which is used for the pressing of this mirror. So this is the glass folded over the stress mirror polishing fixture. So these are the instruments. This is basically the machine which do the grinding and polishing of these telescope mirrors. And this is one of the profilometer metrology tool to ensure that whether we achieved the surface or not. And this is the bonding station, because we cannot directly bend a glass. We need to attach some of this metal structure. So we pasted this metal structure using some epoxy, and we make sure that this is very stiff, so that whenever some force applied to the metal structure, it will transfer the force to the mirror. So with which we will warp the mirror. So this is also one of the metrology tool, which is a interferometer. So as I told, we have a complicated surface. So usually the telescope, one of the segment, it may look like this. You can imagine that wherever the red is there, it is a high point, and wherever the blue is there, this is a low point. So we have to disintegrate this surface into different shapes. So usually an optical profile is described using a special polynomial called Cernicke polynomial. So we decompose this surface into different shapes. So each shape is termed by each name. Suppose this kind of shape we call it as focus. This shape we call it as astigmatism. This is coma. This is trefoil. This is spherical. This is secondary astigmatism. Like this, some 78 different shapes are there. So the idea is we have to each shape which is having kind of a share, like focus will be some 10% of the surface, astigmatism will be 20%, like that. So there is already a prescribed value for each of this shape. So our task is to generate each of the shape into the mirror. So finally we add the entire shape. The combination of the entire shape will look something like this. So this is the basic idea of the stress mirror polishing. So using the stress mirror polishing fixture, we can generate all these different kinds of shape. So like this, like here, it is having some actuators. If you see closely, you can see one actuator here, one actuator will be in the outside. So basically, this will give a differentiated torque value. So because of this particular moment can be generated at the edges. So if you want the inward pressure, you give a more force to the outer and less force to the inner actuator. If you want the opposite, you give the less force to the uh, sorry, more force to the inner and less force to the outer, likewise. So whichever shape you want, you can generate with this SMB fixture. So now the major activities which is happening in the India TMT optics fabrication facility. One is the grinding, polishing, and metrology. So whatever the glass we get, it will be look something like this. So it will be kind of non-transparent. After grinding and polishing, we will have a this kind of very highly transparent surface. Then we do a hex cutting. So basically the segments are in hexagonal shape. So all the segments need to be cut into this kind of hexagonal shape. And we have to generate some of these pockets. There are some pockets for the edge sensor to attach. And there is a central pocket for the segment support assembly to attach. So finally, the segment support assembly will be integrated to the mirror. So this is called PMA assembly. This will then send it to USA for the final surface correction using ion beam figuring, and then we will do a coating. So after coating, it will be highly reflective. So this is the entire process which will happen in the India TMT optics fabrication facility. So these are some of the images we captured during the process. So this is the glass roundel, the glass loaded in the SMB fixture. So we did all the calculation. This is actually controlled by a software. So whatever the shape we want, we can program to the SMB fixture. And this is warped with the particular shape. Then these are the grinding and polishing slurry. We apply the polishing slurry over the glass. Then this is the tool. We load the tool. This is kind of a very heavy tool. Each one weighs around 300 kg. So slowly we have a 3 jack mechanism. So with the jack only we will load the tool over the mirror. We slowly load the tool, and this is the grinding and polishing operation. So after the prescribed duration, we remove the tool and we get the shape like this. After that, we clean the glass and it will get something like this. Then we do a inspection. So any crack or something has happened or not, we do a dark inspection. So this just a video of how the polishing will happen. So basically, there are several steps involved in the grinding and polishing process. So we do two types of grinding. Basically, we do a coarse grinding, which is 4 hours run, and which remove almost 50 micron material. And then we have a fine grinding, which is a 5.5 hour run, which removes almost 20 micron per hour removal. So this is our grinding tool. This is nothing but ceramic tiles, aluminum oxide tiles. So basically coarse grinding and fine grinding, we use this tool. This tool size itself is 1.35 meter. And for polishing, we use this pad tool, which is 36-hour run. Each run is almost 11 hours. 11 hours we continuously need to run this polishing. Then we have a pitch polishing. This is for the final smoothening. So you can see after grinding and polishing how the surface looks like. It becomes transparent. Then after the grinding and polishing, we have to do the metrology. So this is basically a 2DP, 2D profilometer. This is a in situ measurement. So after every process, we have it. This is actually taken up by crane. So this is attached to the crane. So this is the reference sphere. So basically all the blanks are reference to this particular. This is our master sphere. So this, it will take the reference from this master sphere. It will go to the mirror and it will check whether the shape is achieved or not. If not, we have to again do the grinding. And it's kind of a iterative process till we reach the required shape. This keep on going. Then after that, after the mirror is kind of achieved the required surface figure, we do a PM. This is subaperture interferometric measurement. Sorry. Then we have one more metrology called PMM. This is phase measuring microscope. And then we have a CMM. This is coordinate measuring machine, which is for the after hex cutting for the dimensional metrology. So we basically use these 4 metrology tools, and we cover low frequency errors, mid spatial frequency errors, and high spatial frequency errors with these 2 metrology tool, and we check the surface roughness using the PMM. So these are the some of the steps we included. So basically this is our incoming glass roundel. First we do the back surface grind and polishing. So this is the process. After that we ensure the surface roughness is achieved. So after that we take into the bonding station where we attach this bond pad. Then we take this glass into the SMB fixture. Then we do the grinding, and after that it will become very transparent, and it will, after a lot of iteration, we get the required surface figure. Then we do a front surface roughness measurement. After that, now we don't need this bond pad. We will remove this using a debonding station. This is basically done using a induction heater. And then after that, we will transfer into a biop station where we take the 2D profilometer measurement. Then again, after that, again, one more time, we will ensure the surface roughness is maintained. Then this is the final inspection. We take into an inspection rack, and finally we do the inspection for any scratch or chip happened in the surface or not. After this, we will do the, once the roundel polishing is completed, we will go for the hexing and pocketing. So this is actually developed by a company called Optica. It is also based in Bangalore. So they are developing this technology. It is not yet fully proven, this technology. Nowhere in the world this technology is developed. So in India, at least we came to some level. So now we are able to precisely cut this roundel into a hexagon shape. The main challenge is actually we are cutting this glass after polishing. So we are not allowed to have a 200 micron chip size. So that is the challenge. We have to precisely cut this glass. Otherwise, this entire piece will be get rejected. So now the Optica has come up with a process which is 100% proven. So this can be transferred to our TMT mirror also. Then we have segment support assembly. Initially, as I told, this we are not doing in-house. We are outsourcing this work to industries. So one of the industry which is doing this work is L&T Defense Coimbatore. So they successfully completed 10 of this SSA and 5 are already shipped to India TMT optic fabrication facility and 5 are in their facility. So far we have successfully polished 4 mirrors, 3 mirror during our training in US and 1 mirror in our Indian facility. And we have done the hexing and pocketing of full-size mirrors. Then we completed the 10 SSA fabrication. Then we completed the TMT control software and delivered. Other than that, there are a lot of other activities we have completed, but I am not included here. And these are some of the tools and pictures we developed our own. We designed ourselves and we developed within Bangalore. So these are the some of the tools, tool cards for the process. Now, IAA future project. So as of now, we are kind of capable of making our own telescope. So the plan is to make our own telescope in future. So we already got all the technology. We know how to build the telescope. So we don't need any external support for making our own telescope. So with this in our mind, we designed our own telescope, which is a 10-meter class telescope. Because one of the major bottleneck of this kind of project is the fund, because this demands a lot of fund. So even this national NLOT, National Large Optical Telescope, this require as much as fund we contribute into TMT. So almost 1500 crores we need for this kind of project. And another one is NLST, National Large Solar Telescope. This also will come in this. This actually is planned to build in Hanle, and this also is almost near to Hanle. It is in Merak. So these are the 2 future projects within IAA. So with that, I am stopping my presentation. If you have any doubts, you can ask. This is our team which work for the India TMT. We have a small team. We don't have a big team. So the plan is to upgrade the team in future when we go for a full production, maybe in 2025 or 2026. We need a lot of people. We have very few people now. So that's all. So we are expecting all this young generation to join with us in future. Okay, thank you. That's all.
Thank you so much, sir, for that insightful talk. It was truly inspiring to hear from you about IAA's contribution towards the TMT project and the fascinating work you are involved in. Before we conclude the lecture today, I would like to open the floor for a small Q&A session. If the attendees have any questions for Mr. Bashir, please feel free to ask now.
Hello, sir. Can you hear me?
Hello.
Hello, sir. Good evening. Big thanks to you for organizing such a wonderful lecture. So you have shared a lot of valuable insights directly from IIA, to be honest, and seeing the contributions of IIA to the TMT project is really inspiring. So I just have a couple of doubts about the one is about the hexing part. So why don't we polish it after you hex it? And yeah, like if there is a problem about the chip thickness that you are allowed or already, why don't we polish it after hexing?
No, that is actually not allowed. Basically, the surface what we are polished, it get a shape. So if you do one more polishing, it will lose the particular shape. So that is not allowed. So this is not a kind of a regular shape like a spherical and all. If it is a sphere, we can easily get the do a repolishing and all. But this is actually like a puzzle. So if you change one portion of the mirror, it will change the entire shape. So that's why we are not allowed to do. And one more thing, this for the stress mirror polishing, we need the round. We cannot do in a different shape because we have to warp it from the edges. That is one of the challenge. So if you see the similar kind of project, like Europe also have a similar kind of telescope, which is called the ELT, European Extra Large Telescope. So in that, what they use, like what you told, they first cut the mirror into hexagon, then they do the polishing. The problem with that is the always whenever we do the polishing, we don't get the same kind of accuracy towards the edges. So that is one of the challenge. But in our case, even though our edge is little uh, finish is less, anyway we are cutting it. That edge, we call it as edge rollout. That will not be a problem with the TMT. This will be a major problem with ELT mirrors.
And another doubt that I had was about the research in thermal distortion. Does IA actually work on like thermal distortions on the mirror and the disturbances caused by the coating itself on the mirror? Like I reckon they obviously are going to disturb the optical, like the data that you get. So are there any actuators specific to correct the distortions on the mirror?
Yeah. Actually, if you see the segment support assembly, even I told there are three big actuators, right? Which is giving the full size correction, full surface correction. So there are some 18, not 18, 21 warping harness actuators is within the segment support assembly, which we can remotely correct the segment surface. Suppose some deviation happens because of temperature or wind. Up to some extent, we cannot correct it fully, but to some extent of we can correct using this warping harness actuators. That provision is also there. They can ask questions through chat also. If somebody wants.
Sir, this is Naren Karthik. And I have a very basic doubt, sir. Why do we need to do hexing? What is the purpose of it? We could do pocketing directly with a curved mirror, right?
Now the thing is, if you try to combine the mirror of a circular shape, there will be always a gap, right?
Uh,
You cannot.
why not fill these gaps and hexing is a difficult process, no, sir? To
Yes.
cut the mirror, there might be a lot of error. There might be a lot of error. It will not be precise.
Yeah.
Why go for that?
Yeah, that's what, because if you see all the polynomial, the one polygon which is having the compactness is hexagon. It doesn't leave any space. That's why if you see the nature, all the honeycomb structure, they are packed with the hexagonal structure. So we are taking that from the nature. So if you go with any other shape, we won't get that kind of filling for the particular area. So you can ask why can't we go with a square? But square also it has its own uh, disadvantages. So it should be very close to a circle, and it should be a polygon. So when we do all kind of optimization, the best shape which we can do is hexagon. So that's why we always look for a hexagon. You see all the other telescope, they all go with hexagon. And there are some telescope which have the circular mirror like GMT, Giant Magellan Telescope is having a circular mirror which is actually huge. Each mirror is 8 meters. So again they have to do some compensation for the light which is losing through the intermediate gaps. So we always want to collect more light from the mirror. So that's why even hexagon also we ensure very less gap. We have only 2.5 mm gap between the hexagon, so that there won't be any much light leakage through that.
Sir, let's say there is a uh, 10-sided polygon, will it give a better image than the hexagon?
Problem is when you go with a 10-sided polygon, then we put it together, there always will be a gap. If you see otherwise the football structure, they use a hexagon and a pentagon. If you closely watch a football, it has a hexagon, but in between they have a pentagon. So that kind of combination also we can try, but most easy compared to the others, bigger like kind of a octagon and all. Hexagon is the least complicated and most efficient shape.
Thank you for the lecture, sir. It was really good, and I understood the answer to the question, sir. Thank you so much.
Hello, sir. This is Ankur. I also had one. First of all, the lecture was really, really amazing, and like I personally, when you had like sent the abstract yesterday, I personally got interested and started researching about that, and yeah, I found it very interesting myself. So, in one of my question is basically in one of the slides you had discussed about like the decomposition of the mirror surface shape, like right into something called Zernick polynomials, and it has like different components like trefoil, comma, 10% trefoil, 20% astigmatism, right? So, like since each of these like components, contributes different behaviors to the overall like optical profile. So, like, don't we have like a risk of like phase misalignment or like some interference in that? Like,
So
wouldn't
that's
these
one.
components be
Yeah,
interfere with each other?
yeah, that's one of the beauty with this Zernike polynomials. It is actually orthogonal polynomials. So by theory, if you alter one of the polynomial, it will not affect the other polynomial. So this will not interfere between each other. That's one of the reason they are using the Zernike polynomial to describe the surface. There won't be any interference in theory. Practically, it's kind of different that we are experiencing a lot of problem. But at least from the theory side, this is orthogonal and this will not interact with the other polynomial. So if you go through the Zernike polynomial, you can see the derivation. Each one is like rho cos theta, one will be rho square cos theta. So all are kind of orthogonally separated. So by principle, it will not interfere. That's the basic idea.
All right,
A
so
good
one more
question
question
actually.
was like, yeah. So one more question, actually basic question only, but
Yeah.
like the monarchia was selected like really after a lot of debates and like lot of issues. This was selected as the uh, like the ideal location, and the construction started in 2014, and then it was disrupted, right? And so,
Yes,
what
yes.
could be the like main reason? Yeah, even we had like in the list of potential sites for installing this telescope. I think we even had Hanle Ladakh, right? So, like, what could be the like potential reasons why site has been chosen particularly? Like, is there any
Yeah.
geographical? Yeah.
Yeah, exactly. Yeah. So when we select a site for the telescope and which is the best telescope we want to build, so we always look for the best site, right? So in terms of the clear sky and the altitude, there are a lot of factors which affect the seeing of the telescope. So suppose if we make a telescope in Bangalore, I'm just saying, it is kind of non-usable because Bangalore is kind of lot of light pollution is there. So always we look for a place which is kind of very well deserted and which is very minutely affected by the light pollution. So that's why if you see all the telescope, it will be very far away from the civilization. So that's why we made our telescope in Ladakh, where the sky is absolutely clear. You can even see the Milky Way with our bare eyes. So always we look for the better sky, better location. So when we categorize, when we ranked all the sites, we took some 5 sites all over the world. So Hanley was the 5th best, and Mauna Kea was the 1st, and we have La Palma as the 2nd. So that's why we always wanted to go with Mauna Kea, Mauna Kea, because that is the best sky you can get. You get more than almost 300 clear nights. Each night is money. Like we say, time is money. Each night is money. If you get one extra night, that gives you extra income, or it makes your effort worth. Always people try to maximum utilize the sky, and get 1 day extra data can make one PhD. That's the kind of thing. So Mauna Kea, and the main problem is so
Thank
the
you.
yeah, no, I will tell one more thing. The main problem with the Mauna Kea is the location or the site identified for the Mauna telescope. It is considered as the one of the sacred place for the local Hawaiians. So they consider it's like a kind of a sacred place. They do all their puja kind of thing. So they even doesn't go to that particular location, because they find even putting their feet on that particular location is kind of will affect the sacredness of that area. So that kind of religious emotions were there. So that's the one of the major uh, disadvantage with that particular location. But it had been there always. Already there is 13 telescope in that Mauna Kea Island. So always there was problem. So somehow they sorted out all these things. But this time it was very dramatic. So when I joined in IAA in 2015, it was told that the first light telescope will be operational from 2024. Now we are in 2024. The estimated time is 2035. We don't know when exactly it will go. So in case it doesn't go there, we have a alternative site in La Palma, which is in Chile. So let's see. Hope for the best.
Thank you so much. Does anyone have any other questions? You can uh, either unmute yourself and ask, or put in the chat box.
No more questions. Shall we wind up the session?
Okay. Okay. So before winding up, I wanted to ask one more question. It is a bit off topic, but I wanted to inform the audience that Bashir sir himself is a like multilingual person. He knows a lot of languages: English, Hindi, Kannada, Tamil, Malayalam, even Arabic and Dutch. So like that's a lot of languages, and that's quite impressive. So like I'm really interested to know how you could speak so many or understand so many languages. So.
I am fascinated by languages. Being a Keralite, one of my problem was language. So when I came out of the BTech, I was not at all uh, good with English also. So I was very scared to speak a new language. I know English, but still I had that fear to speak. Then when I went to the IST, so within some 2 3 months, I learned Hindi, because all my friends, like we had 4 boys in our class. So out of 4, 3 were North Indians. So I was forced to learn their language. So like that I learned. Then I came to Bangalore. So as a Keralite, I know a little bit Malayalam. And here I am trying to learn. Not I am not telling I am 100% fluent, but I am trying to learn all this Kannada. Even I tried to learn Dutch also because after MTech I wanted to do my PhD in Netherlands. So for that purpose I learned Dutch for 1 year, but now I forgot completely. I haven't tried it. So like that, it's our necessity. When the necessity comes, we all automatically learn the language.
Right, sir. All right. So Gautam will be winding up this session. Yeah.
Thank you, everyone who those who participated in the Q&A session. Sir, it was truly been an honor having you with us today. Your talk has been highly inspiring and might have sparked interest among a lot of us, and I'm sure many of us would be more motivated to explore these fields. Once again,
Right.
on behalf of entire Nakshatra team, we are incredibly grateful for having you with us today and for sharing your knowledge and insights. We hope to stay connected and hear more about your future endeavors. Thank you all and have a great evening ahead.
Right. Okay.
All right, sir. So I think we can end the meet, right?